take I'm going to take an example of an integral across gamma of 2z dz. And if, and here we're going to say gamma is the line segment from -3 to 3. Okay, so if you do that, then so this one has an antiderivative, right? So it's z squared from -3 to 3. So that's going to be 3 squared minus -3 squared. So that's going to be 0, right? Okay, so that one you can. And also, surprisingly, if you take it across, let's say, sigma, and let's say sigma is a semicircle, also from -3 to 3, so we're going this way like that. So sigma is this semicircle here, and the same function that's going to give you the same result. Okay, that's going to be 0. Okay, now let me show you an example where this doesn't work. I'll show you a couple of examples where this doesn't work. And the thing about it is, okay, this gamma is still the line segment. The thing about it is, in complex variables, you can write down functions that don't have antiderivatives. Like this one does not have an antiderivative. Okay, this modulus of z squared, or modulus of z, it does not have an antiderivative. Okay, so, and you know that it's not holomorphic too, because if you try the Cauchy-Riemann equations, it's just not going to work. Okay, so what you have to do there is you have to actually parameterize the curve. And so let me see, from -3 to 3, see, we can parameterize that by gamma of t equals, so 3 is the ending point, and then, wait, let me do it in order. So the beginning point is -3, so you can go like that, and then plus 3t. Which simplifies to, if you distribute the -3 in, you're going to get, well, you're going to get 3t, so it's going to be 6t minus 3. And so that's a parameterization. So then gamma prime of t is 6. So then to do this one, what you have to do is so this z gets replaced with this gamma of t, so this 6t minus 3. And the dz gets replaced with 6. Okay. So let me just make a note of that. So gamma of t goes in here, and this one gets replaced with gamma prime of t dt. Okay, so that's 6 dt. Okay, and so then this is how you would calculate this integral here. So what is that? Dang, I made this unnecessarily nasty. Okay, so this is 36 t squared. Now you can take an antiderivative of this at this point, because you're down to just the variable t. So you're just down to one variable instead of two variables. 6t minus 3 minus 36t plus 9. That's all times 6. Oh, dang. I think I chose a really bad example. Okay, let's do it anyway. So this is going to be, if you integrate that, you get t cubed over 3, that's 12t cubed minus 18t squared plus 9t evaluated from 0 to 1, all times, all multiplied by 6. Right, so that's, put the upper limit in, so it's 12 minus 18 plus 9 minus, and put zeros in, that's all going to be zeros. Okay, so that's 6 times 3, 18. So 18 is your answer there. And then another example is let's suppose that you were just supposed to go gamma y dz. Okay, so by that, I mean, y is the imaginary part of z. Okay, so where z is, the variable is x plus iy, right? Okay, so if you're across this same path, then what would happen is we would get, since basically you can say 0i right here, that means that your z is 0. So that interval is going to be 0 if you do that. Now, if you're integrating x, then you would put this in. Yeah, so if you're integrating x dz, then you would put all this in because this is your real part, right? And then so you calculate that. But let me see. I guess you could still make an argument that like if you treated this as an x squared, let me see. If you integrated this x squared, you get x cubed over 3, right? And you plug in the upper limit and lower limits. You still might get 18. But that's not really taking a legitimate antiderivative. Okay, let's try this. Let's try to integrate this one over the semicircle. Or maybe that would be too nasty. Okay, so sigma, the semicircle, you could parameterize that. So it's just going to be this semicircle right here, right? So you could parameterize that. So we're looking at this right here. That would be 3 e to the it. And then you could say that you could let t go from pi back down to 0. So this is kind of looking backwards, but this really works out really nicely. Okay, now and then gamma prime of t would be 3i e to the it. Just taking the derivative of that. So the integral of the modulus of z squared dc is going to integrate from pi back to 0. You're allowed to do that way. What's the modulus of this? What's the modulus of 3 e to the it?
3.
Yes, that's right. So it's 3. So the modulus squared is 9, right? And then you have this 3I e to the it part, right? dt. Okay. So this is going to be integrating. What's an antiderivative for the e to the it? Or I e to the it, even better.
E to the it.
Over IT, over I.
Yeah, e to the it. Excellent. Okay, because the derivative here, when you take the derivative, it's going to be e to the it times the derivative of it, which is just I. So you'll get that I right there. Okay, and so that's going to be evaluated from pi to 0. So you plug in the top limit first, e to the 0 minus 27 e to the pi I. So plugging in 0 first, that's going to be 27 minus, let's see, what's this going to be? E to the pi I is -1. And so that's going to be 54. So notice that you go along different paths. Here, going along this path, you're going to get, going along this path from -3 to 3, the line segment, you're going to get 18 as your integral. But if you go across this semicircle to get there, you get 54 as your integral. So a big difference. There's a difference. It's a different according to the path, according to different paths. Whereas if your function that you're integrating is holomorphic and has an antiderivative, then it doesn't matter what path you take. It's just going to be the same either way. You can use the fundamental theorem of calculus. Okay, so hopefully that clears up a few things. If we were to try this one, that would be pretty nasty, because what you'd have the y part is actually, if you take that, it's going to be cosine t plus I sine t. So the y part is going to be I sine t. I sine t. So that's 3I sine t right there. And then you still have this to deal with, e to the I times I e to the it. So that it's an integral that you can do, but it will take a while. So we're not going to do that now. Okay. Let's see, where were we? So one thing I wanted to point out right here was corollary to 420. If you have a holomorphic function and it's piecewise smooth and gamma is homotrophic to 0, well, what's going to have to happen is it's going to have to be gamma is not simply is closed. Okay, so that means you can just like, so gamma is completely inside of Z, and then F is holomorphic in G also. So gamma is completely inside of G. Okay, here we got it's going in a negative orientation, and let's say this is G right here. So that's G, and gamma is completely in there. And you can, by staying in G, you can like shrink this down to nothing without passing through any singularities of F, without passing through any points where F is not holomorphic. I mean, then the integral of f is going to be 0. Okay. So this is
Doesn't mean
basically,
if it is.
what's that?
Oh, I mean, doesn't mean if it is inside G, then it will be closed, or it has to be closed as well, even though if it is inside G.
Has to be closed.
Okay.
Okay. So this is really something that follows from so if you have this curve right here, let's say you got a curve going like that around there like that, and if you parameterize that curve, you'll get something, and then you'll have t being like this, right? And what's going to have to happen is you're going to have so closed. Okay, closed means that gamma of A equals gamma of B. So that means that the starting point and ending points are the same. So what does that mean? So that as you go around here, you come back to the same spot. But what happens is if you have a function that's holomorphic, then you will find an antiderivative of it. And if these are the same, then those points are the same, which means that this is the same as that, which means if you take something and subtract itself, you're going to get 0, right? So that's where this comes into play. Okay, but you have to be careful. Like last time we said, like for example, here's the logarithm. Okay, and it's not holomorphic on the negative row axis, right? The logarithm is not holomorphic right there, but it is holomorphic everywhere else. So if you take an ellipse up here, and that's your gamma, then this is a simple closed curve. That means this thing's going to happen, and your integral is going to be 0 across this curve, across this path. Okay, so does that help clear things up? Hope so.
How about exponent? Is exponent homomorphic the whole complex plane?
Yeah, the exponential function is holomorphic everywhere. It's entire.
Okay.
So, so exponential of z, that's entire. So is sine z, and so is cosine z. And also the hyperbolic sine and hyperbolic cosine, because those are just completely, they depend on exponential of z. So those are examples of entire functions. So, and then also polynomials. So any polynomial is entire. Okay, so if you integrate any of those along a simple closed curve, you're going to get 0. If gamma is closed, I'm sorry, if gamma is closed anywhere, if gamma is closed, your integral is going to be 0. Okay, I wanted to talk about another function. Let's see here. So let's take, So let me talk, so the things that give you problems is, maybe I should classify. Those are entire, there's no problems at all. Okay, if you have a function where you have like z minus z naught in the denominator, then this is going to give you problems that that's not holomorphic at z naught, because that's like in the denominator, right? So that's going to give you trouble. Okay. If you have log of z, then that's going to be not holomorphic right here. So that part's going to give you trouble. Okay. If you have z to the 1/2, then this one, the way that it's defined is exp of 1/2 log z. Okay, so this one is the same problem as log z. So for that, you have to watch out. You have to watch out for that. Okay, like if you have well, let's see here. Yeah, so if you're raising it to a fraction like this, then you have to be careful about the negative roll axis. Okay. And so, for example, let's say you want to integrate this guy right here, z to the negative 1/3, negative, what the heck, what am I doing? I meant to write negative 3/2. I meant to say and write negative 3/2, but I said 1/3 instead. I don't know how that happened. Okay, so when you have something like this, you have to worry. If your curve goes through here, then that's problems. You just can't do it. Well, yeah, you just can't do it. Okay, if it's going to cut through the negative roll axis, then that's a problem. Or you can split it up into two pieces probably, but we'll try to avoid that for you. So if we said though that gamma is the line segment from 1 to 1 plus 2i, if we just say that, then we can do it, because gamma is going to go from 1 to 1 plus 2i. So gamma is going to be right here, right? That's going to be your gamma. And you only have to worry about stuff over here. This is what you have to worry about over here. And since this is over here, it doesn't cross through there, then you're good. So then you just say, okay, well, I applied the rules from before. So the integral, so raise this by 1 power, and then multiply by the reciprocal of this, which is -2. Okay, so when you take the derivative of this, you have a negative 1/2 comes out, which cancels that off. And then this reduces by, this is subtract 1 from that, you get -3/2. So that's fine. And then you just say 1 to 1 plus 2i. Okay. So then, but it's going to be kind of hard to calculate this. What is it? 1 plus 2i to the 1 over 1 plus 2i to the 1/2. And then minus putting a 1 in, you get +2. So you'd have to evaluate this, which is certainly doable. And probably just find the principal value of it, of this. Okay. Okay, so that's another thing you have to worry about. And then you also have, and then lower down on the totem pole, you have things like the modulus of z, the conjugate of z, the imaginary part of z, or which is y. And then you have the real part of z, which is your x. You have these functions, and these are not homomorphic anywhere. Okay, so if you see something like this, then okay, we're going to use this rule right here. If you see things like this, then you have to worry about, okay, is it going to passing through a singularity? And then if you see things like this, then you have to just use the original formula, use the definition. You can't, because they're not homomorphic anywhere. You can't just like, oh, try to pretend that you know what the antiderivative is, because you're going to get it wrong if you do it that way. Okay, and then there is another case, which is really important, and it's actually this case right here, not another case. It's this one right here. When you have this is a very important case. So let me talk about this for a little bit. Okay. So I'll start with an example. Gz over z squared minus 1. Okay, now, one technique is partial fractions, because we know that this factors into z minus 1 and z plus 1, right? So you guys are familiar with partial fractions, right? Now, if you multiply by this factor here, both sides, you're going to get this. And then if you set z equal to 1, then that goes away. You get a is equals 1/2. And then if you set z equal to -1, that goes away, and that becomes -2. So b is -1/2. Okay, so really this integral becomes the integral of a over z minus 2 plus the integral of b, which is, I guess we could say, let me change that to a minus. So minus 1/2 over z plus 1. Wait, what did I put a 2 there for? Okay, z minus 1, z plus 1. Okay, so I'm going to look at a few different examples here. So let's put this up by 1. So we have, or let's call this example 1. As to what gamma is, so that you notice I haven't defined what gamma is. So where is this not holomorphic? Based on what I said, where is this not holomorphic?
Is it when z equals to 1?
Yes, when z is 1, and where else?
-1.
Yes, and -1. Okay, so those two places is where z is not holomorphic. Okay, so if gamma is some curve like this, then the integral is going to be what?
0.
Yes, that's going to be 0. Good. Okay, now, example 2. What if gamma is over here? So gamma goes around, it goes around the 1, but doesn't go around the -1. Okay, so that's I can split it up in these two pieces right here, right? There should be a DZ there. Okay, so what is this integral going to be? Around this gamma. What's that integral going to be?
That would be 0.
That's going to be 0 because it doesn't enclose this point. Okay, now does anybody remember what this integral is going to be? Nobody remember what that's going to be? Anybody remember? No one remembers?
Is that natural log?
What's that? It's not natural log. It's a number. It's a imaginary number. Like, that's a good hint. That's a big hint. Okay, let me work it out for you, okay? So it's going to be the same as if we drew a circle around with the positive orientation. Okay. And the circle could have center 1 and radius. It could have radius 1 or radius r, doesn't matter. As long as it's less than, well, it doesn't matter because we're only looking at this one. We already decided that's 0. So this one, the point is that this one you can deform the curve. We talked about that last time. So you have this weird shaped curve right here, right? But you can make it into a circle. Okay.
Oh, is that?
And it's still going to give you the same integral. Yes, this is 2 pi I. So we did this before previously. You can go back and look it up. You're gonna have to do it in the homework. But again, the parameterization will be 1 plus. Well, let me make this an r, okay? I'll make it, and then r e to the it, and then you'll have t going from 0 to 2 pi. Then that's the parameterization I'll use, and then just apply the definition. You're going to get 2 pi I. Okay, so that one's going to be pi I. Now, another one, example 3. Let's suppose that we do this. Ooh, that's like an infinity curve, right? Unless they were going this direction. So we're doing like a figure 8 on its side, or an infinity on its side. Okay, and let's let that be the gamma. Okay, so what is the integral of gamma of this? Okay, so what's this integral going to be of this first one? So you basically, this is basically like two simple closed curves, as this one and this one. Okay, so this first one, where you're going around 1, right? So that's going to be 2 pi I, right? Okay, now what is the second one going to be? This one over here at -1. Here's -1. And this is the singular point, or the point where this is not holomorphic. The only point where it's not holomorphic is at -1.
Is that something like negative 2 pi?
Yes, it's negative 2 pi I. Okay, do you guys see why it's negative 2 pi? Because we're going backwards. We're going in the counterclockwise direction. We're going in the clockwise direction here, around the negative 1. Here we're going in the positive orientation, around the 1. So that's positive 2 pi I. But here we're going in the we're going in the negative direction, or the clockwise direction, which is negative. And so the answer is negative 2 pi I. Okay, and so that's going to be pi I plus pi I. That's going to be 2 pi I as the answer to that. Okay. And then if you enclose both points, so if you just have a curve that encloses both points, then that integral is going to be 0, because then you'll have this 1/2 2 pi I plus, and then you'll have, or I'm sorry, minus 1/2 of times positive 2 pi. So those will cancel. You'll just get 0. Okay, so those are some examples there. Okay, now let me modify that a little bit. So what's your favorite holomorphic function? Anybody? You like exponential functions, or do you like the sine or the cosine?
Exponential.
Okay, good. Let's go exponential. And we'll say exponential of, do you want to put, how about we put a z squared? Okay, and we'll have that over, and then we'll have it over z minus 1, okay? Okay, so this is, if these were x's, this would be really challenging to integrate, right? This would be pretty nasty. Okay, but in complex numbers, so this is the only place where it's not holomorphic 1, right? It's holomorphic everywhere here. So let's do this. Let's have gamma be a curve that encloses this, that it encloses 1. Okay? Let's say that's gamma. Okay, and let me show you what you can do with this. You can, okay, so so this looks pretty nasty, right? That looks pretty nasty. Yeah, for sure that's nasty looking. And you don't even have a formula for gamma, right? However, you do know that, okay, so if we, let me do this. Let me blow things up, okay? Imagine that your 1's right here. And imagine that this y-axis is like, is somewhere to the left, maybe like a mile away, okay? Or a kilometer away, okay? Because you guys are metric system people. Okay, so imagine that, okay, so imagine that the y-axis is that direction 1 kilometer, okay? So what does that mean? That means this is incredibly magnified. We're looking at this under a microscope, basically. Okay, and then and we'll say sigma is this right here, is this curve. Oops. That's sigma curve. And so basically, if we were to look at it here, it would look like a little teeny, maybe even smaller than that, okay? Okay, based on what we said before, because this sigma is in the same direction as the gamma, and it encloses this point, it doesn't like, as you can think of gamma as shrinking down to sigma, it never crosses any points where this function is not holomorphic. It only passes points where this function is holomorphic. Okay, so that means that this integral is the same as that one. Now, if you keep on shrinking down, then what happens is as sigma shrinks down to, as gamma shrinks down to sigma, and then you just keep shrinking more and it shrinks further, all points on the curve converge to 1. So that means that all points at f of z on the curve are going to exponential of 1 divided by 1 minus 1. So the numerator is going to that. Okay, so the point is, what happens is this is really going to the exponential of 1 squared over z minus 1. Okay. So you can make an argument. So I don't know, you see what I'm trying to say here? That as you shrink this curve down, all the points on the curve are converging to exponential of 1 over z, or well, 1 minus 1. That's kind of weird though. We'll leave that as z minus 1. So all these points are converging to the exponential of 1. Okay, so this is not, as by no means a mathematical proof. You can look up the proof in the book. I'll show you in a minute. But this is kind of just a rationale for what I'm trying to do, what I'm trying to show here. And this is really e to the 1, right? Just e to the 1. Okay, so basically just have e to the 1 times this integral here. And what's this integral here? It's 2 pi I, right? Okay, so this integral is actually going to be 2 pi ei is the evaluation of that integral. Okay, now you can do this because this top part is holomorphic, which implies continuous. Okay, so continuous, so you're good to do that. What's that?
If the point changed to 2, would it be exponent of 2? I'm just making sure if I understand it. Or it's always 2 converts to 1.
Okay, so you're saying if, let's say you had a curve and you had, and if this was a z minus 2 in the denominator, is that what you're asking?
I was actually asking
if
the circle is like, yeah. Yeah.
And the circle is around 2. Yeah, then what's going to happen is that's going to be e to the 2 squared times 2 pi I.
Okay.
Okay, so that'll be 2 pi e to the 4th I. That would be the answer there if that happened. If you're around 2, and it's a z minus 2 in the denominator. Okay. Now, on the other hand, if your curve does not enclose the 1, then it's going to be 0. Okay, this right here is Cauchy's integral formula. Okay, notice in the example that we had an exponential of z squared, and then you have a z minus, we had z minus 1, and then we changed it to z minus 2, right? And then we didn't have the circle, we had something else. So basically, another way of looking at this is as this, 2 pi I f of w. This is the way that I just showed you how that works out. Okay, here they have a circle with center w, radius r, with positive orientation. However, let's see here. However, it later changes to this. It just has to be, okay, it just has to be a positively oriented, simple, closed, piecewise smooth path. And W is inside gamma. Okay, F is holomorphic in the region G. Okay, then you have that. Okay, which translates to this right here. Two pi I f of W. Okay. It's supposed to be equal. Fix that. Okay, let's see. Okay, let me show you another way to, so that's kind of like what we just did. So that's what we just did, right? We did an example of that, of how to find an integral like this using Cauchy's. So Cauchy's integral formula is really important. And we showed an example of how to do that. Also, there's an alternative way to do this problem right here, which doesn't involve splitting it up into, it doesn't involve having to find the partial fraction decomposition. So let me show you that really quickly. Okay, so the problem was this right here. So you have the integral over gamma of dz over z squared minus 1 for various situations. Let's just take one of those situations. And we know that the singularities are at -1 and 1. So let's just take the situation where you're going around 1, okay, like that. Okay, so let's suppose we're doing that kind of a thing, right? Okay, then what happens, what you can argue is that this denominator is z minus 1 times z plus 1. Okay, the z plus 1 is not a problem, so you can pull that to the numerator as a 1 over z plus 1, right? Okay, so that right there, and then dz. And so then in Cauchy's integral formula, your f of z is 1 over z plus 1. So this is going to be 2 pi I times f of 1. Okay, so your w is your 1, right? Which is f of 1, just put a 1 in here, you get 1 over 2. Okay, and then so you get pi I, which is the same answer that we got before. And if we, let me do one other one. Okay, so let's suppose that your gamma is, let's suppose your gamma is this one, like that. Then, since this is the counterclockwise orientation, you can basically look at it as if you're going around each of these singular points separately. Okay, you can think of it as going around each point separately. And it will be the sum of two integrals. And in the first integral, you'll be going around like this really small circle centered at 1 and really small radius. And the second one, you'll be going around -1 with a small radius. And this one would be 1 over z plus 1 over z minus 1, because that's where your singular point is, or your point where the function is not differentiable, not holomorphic. And then this one would be 1 over z minus 1 over z plus 1, about the -1. Okay, and then so this becomes, if you plug a 1 into here, that's 1 over 1 plus 1 times 2 pi I. And then this one is 1 over -1 minus 1 times 2 pi I. Okay, so this is pi I, and this is going to be minus pi I. That's going to be 0. Okay, so that's an alternative way to do this. So let me do another example along those lines. Okay, let's suppose that we're integrating in the numerator, let's put the exponential function times the sine function. And then the denominator, let's go z times z minus 2. Hold on. Let me make this the cosine, because I don't want it to be, I don't want it to be 0. So it's cosine z. So exponential z times cosine z. And let's make it a circle with center 0 and radius 3. Okay, so when you do these problems, it's really important to draw a picture of what's going on. So if we have the axes here, where are the singular points? Where are the points where this is not holomorphic?
0 and 2.
Yeah, so 0 and 2. So there's 2. And then this circle encloses both, right? So it's radius 3, it's something like that, right? Okay, so what you can do is you can set it up as two, you can split this up as 2 integrals. The first one will be over a circle whose center is 0 and radius, we'll say radius 1. And the second one could be over 2 and radius 1. So it's centered at 0. Okay, so this circle here would be right here. And this circle here would be over here. And actually they touch each other. Oh, this is bad. Oh well, something like that, okay? But they actually touch, the circles are gonna touch if we have the radius as 1. We make the radius 1/2 or we make it less than 1, okay? Then that's gonna be the same thing. Okay, then over here with this first one, the z is the only thing that's going to be even the denominator. Okay, and everything else you take to the numerator. And here, the z minus 2 is all that you leave in the denominator because that's the only point that's enclosed by that. Okay, and then the numerator becomes exp of z cosine z over z. Okay, great. So what's this integral going to be?
It's like e over -2.
Wait, what? Let's put the 2 pi first, okay? And then what's this part going to be?
Yeah, e over -2. Is that?
Yeah, well, e to the, let's see, actually e to the 0, cosine 0 over 0 minus 2. Yes, like that. These are both 1, so it's going to be 2 pi I over -2, so that's negative pi I, right?
Mm-hmm.
Yeah. All this becomes negative 1/2, and so then it's negative pi I. Okay, and then this piece right here, that's another 2 pi I. But then what do you have here?
E to the 2 times cosine 2 divided by 2.
Yeah, you just plug 2's into here. Okay, so your W is 2, and your F of W is this. You're just plugging 2's in for Z's right here. Okay, so that's going to be plus, the 2's are going to cancel, and you're going to have pi times E squared cosine 2I. Whoa. Great, so that's what the integral is going to be. Okay, so that's the Cauchy's integral formula right here, and kind of some applications for that. And then we get to the exercises there. I think that you'll be able to do the exercises pretty well. Oh, let me say one more thing right here regarding this problem. Or let me do a little variation on this, and then that'll be it for the day. So here our curve was this going this way, right? This. Okay. If this curve had gone the other way, the negative orientation, then everything would just be negative. So this would be positive, and that would be negative. Okay. Another thing that could happen, which you have to pay careful attention to, is this. Let's say, so we have an integral. We have the same function as before, which was exponential of z cosine z, and then we have z times z minus 2 dz. Okay, so if so here's 0, here's 2. So if our curve, if our circle, if instead of this one we had the circle with center, we'll give it a center of 3 and a radius of 2. Okay, so if that was our circle, then the center would be over here at 3, right? And the radius would be 2, which means it comes to here. Okay, and then sometimes you put a plus there, meaning the positive orientation. That means it would go like this, right? It doesn't include the 0. The 0 is not inside the curve. Okay, so that means that the integral is just going to be so that means you look at the integral this way. And so what's the integral going to be here now?
Two pi I times e to the 2 and cosine 2 divided by 2.
Exactly, yes. So the 2's cancel, you get pi I e squared cosine 2. You just get that. So you don't have the other piece because you're not enclosing the 0. And then of course, if you had let's say you were going over a curve like this, let's say this curve's over here. Let's say that's your gamma. What would this integral be?
0.
Yes, that would just be 0. Okay, so if it doesn't include these points, then it's going to be 0. Because 0 and 2 are the only places where it's not holomorphic. That would be 0.